This problem is from GATE Mechanical Engineering of 2019. This is question number 31 of set 1. The question is, the rotor of a turbojet engine of an aircraft has a mass of 180 kg and the polar moment of inertia is 10 kg meter square about the rotor axis. The rotor rotates at a constant speed of 1100 radian per second in the clockwise direction when viewed from the front of the aircraft. The aircraft, while flying at a speed of 800 km per hour, takes a turn with a radius of 1.5 km to the left. The gyroscopic moment exerted by the rotor on the aircraft structure and the direction of motion of the nose when the aircraft turns are. So we are given 4 options with the value of gyroscopic couple and the direction of motion. Let's understand the gyroscopic moment for this problem. Now let's assume this is an aircraft with turbojet engines. Usually there are 2 turbojet engines in an aircraft. So we will take the combined effect of these 2 turbojet engines in the front. So in the problem it is said that when we view from the front end, the rotor seems to be rotating clockwise direction. That means this is the front, or I can say the nose or front, and this is the tail of the aircraft. So from this view, if see from this side, we will see that the engine or the fan is rotating in clockwise direction. So it will be rotating in something like this. Now for this rotor, this yaw axis will act as a precision axis. Now because of this clockwise rotation of the rotor, when viewing from the front, it will generate an angular momentum in the backward direction using the right hand thumb rule. So the direction of angular momentum will be in the opposite side of the motion of aircraft. So this will be, let's say, L0 angular momentum, initial angular momentum that is generated because of this rotation of the rotor. Now it's given that the aircraft is taking a left turn. That means aircraft is taking a turn in this direction, left direction, right, from the axis. Now this is the axis. So if this is the axis, the aircraft is taking a left turn, right? Now to take a left turn, the aircraft will apply an angular momentum in the opposite direction, that is in this direction. So this is Ln vector. So new angular momentum, because the aircraft needed to turn in this direction, in the back side it will apply this. At the same angle, it will apply an angular momentum. Okay, so now this is the new angular momentum. Now since there is no external torque present, the change in angular momentum should be 0. So there should not be any external angular momentum, right, from the conservation of angular momentum. Now in order to adjust this angular momentum, so this new angular momentum, the plane will apply a torque in the right. So in the right, the plane will apply a torque. And also, since we need to conserve the torque, there will be a torque in the left direction as well. So let's write tau L. Now this tau R is utilized in changing the angular momentum from L0 to Ln, the new angular momentum. So it will adjust this angular momentum in left direction of the aircraft. So this tau R will be utilized here in this change delta L. Now this tau L vector, what it will do, it is called this is the active gyroscopic couple. Now this will produce a reactive gyroscopic couple that will lift the tail of the aircraft. So this will be the reactive gyroscopic couple. So let's say C R. So this is a reactive gyroscopic couple which will lift the tail of the aircraft. That means it will bring down the nose of the aircraft. Therefore it will bring down the nose of aircraft. Now let's calculate the gyroscopic moment exerted on the aircraft. So in the problem it's given the mass of the aircraft, let's say M, is 180 kg. The polar moment of inertia, let's say I, it's given 10 kg meter square, and the rotation speed of the rotor is given as let's say omega r is equal to 1100 radian per second in clockwise direction when viewing from the front. Also, the speed of the aircraft is given as 800 km per hour. That comes out to be 222.2 meter per second. We just multiply it by 5 by 18. And the radius of turn is also given, that is 1.5 kilometer. That's nothing but 1500 meter. Now the angular momentum of the rotating aircraft is given by L is equal to I into omega. Now the change in this angular momentum, delta L, can be written as L into delta theta. Therefore, this delta L will be equal to, now we will substitute this value. So this is I omega delta theta. So the rate of change of angular momentum is nothing but the gyroscopic couple. So let's write for gyroscopic couple C is equal to dl upon dt, and that will be equal to limit delta t tends to 0 I omega delta theta by delta t. We have substituted this value from here. Therefore, the gyroscopic couple will be equal to I omega d theta upon dt, because delta t is tending to 0, and this d theta by dt is nothing but d theta by dt is the angular velocity of precision. So let's write omega p. So we have got the formula for rate of change of angular momentum, that is the gyroscopic couple, that is C is equal to I omega, that is omega r, speed of the rotor, and d theta by dt, that is omega p, angular velocity of precision. Now using this formula, let's calculate the gyroscopic couple. So we can substitute the value here. I is given 10, omega r it's given in the problem 1100 radian per second into omega p. Omega p is d theta upon dt, that is v upon r. R is the radius of turn, so this will come out to be 10 into 1100 into v. V is given as 222.22 meter per second divided by 1500 meter. You can perform this calculation in the calculator, and the gyroscopic couple will come out to be 1629.63 Newton meter. Now let's go back to our problem and check with the options. So here the option, because the aircraft nose is going down, so this option A and option C is incorrect. Now the value comes out to be 1629.6 Newton meter, so option B is the correct choice here. Now to get more information on gyroscope, such as the derivation of gyroscopic couple, you can follow the NPTEL course on gyroscopic action in machines, a lecture series on dynamics of machines by Professor Amitav Ghosh of the Department of Mechanical Engineering at IIT Kanpur. Hopefully I was able to solve your doubt. Have a great day.